Hello everyone. Welcome to this video. Today going to learn about parity. But before I tell you what parity is, let me ask you a question. Have you ever sent a text message and it arrived with a typo that you did not make? Or have you ever downloaded a file and it got corrupted? Computers face this problem all the time. When data travels from one place to another, errors can happen. So how does a computer know if the data it received is correct or not? That is where parity comes in. Parity is a very simple idea. Are you ready? Parity just means checking whether the number of ones in binary data is even or odd. That is it. Even or odd. Let me give you an example so you understand clearly. Look at this binary number. 101. How many ones are there? Let us count together. 1, then another 1. That is 2 ones. 2 is an even number. So we say this data has even parity. Now look at this binary number. 1011. Count the ones. 1, 2, 3. 3 ones. 3 is an odd number. So we say this data has odd parity. That is literally all parity means. Even number of ones or odd number of ones. Nothing more. No hidden complexity. But here is the clever part. If the sender and receiver agree on a rule beforehand, they can use parity to detect errors. For example, they can agree, we will always keep the number of ones even. Then if the receiver gets an odd number of ones, they immediately know something went wrong. In the next slide, I will show you exactly how we add an extra bit to make this work. Let us move on. Now that you understand what parity means, let me introduce the parity bit. A parity bit is one extra bit that we add to our binary data. Just one. Either a 0 or a 1. Why do we add it? To make the total number of ones either even or odd, depending on the rule we choose. Think of it like this. Imagine you are packing a suitcase for a trip. You want the suitcase to weigh exactly 20 kilograms. But your clothes only weigh 18 kilograms. So you add a small extra item to make it 20. That extra item is like the parity bit. The parity bit completes the data to follow the rule. There are only two types of parity. Only two. Type number 1, even parity. Even parity means the total number of ones, including the parity bit, must be an even number. Type number 2, odd parity. Odd parity means the total number of ones, including the parity bit, must be an odd number. Let me repeat that because it is important. Even parity wants an even total. Odd parity wants an odd total. Here is a quick example before we go deeper. Suppose your data is 101. That has 2 ones. Even. If you are using even parity, you want the total to stay even. So you add a parity bit of 0. If you are using odd parity, you want the total to become odd. So you add a parity bit of 1. See how the same data gets a different parity bit depending on the rule. In the next 2 slides, I will walk you through odd parity and even parity step by step with real examples. Do not worry. You will master this in no time. Let us start with odd parity. The rule for odd parity is very simple. I want you to say it with me. Total number of ones must be odd. Good. Now let us see how this works with a real example. Here is our data. 1011001. Let me write it clearly. Positions. First bit 1, second bit 0, third bit 1, fourth bit 1, fifth bit 0, sixth bit 0, seventh bit 1. Now we need to count the number of ones. Let us do it together slowly. Bit 1 is 1. That is 1. Bit 2 is 0. Not a 1. Bit 3 is 1. That is 2. Bit 4 is 1. That is 3. Bit 5 is 0. Not a 1. Bit 6 is 0. Not a 1. Bit 7 is 1. That is 4. So total number of ones is 4. 4 is an even number. But remember, we are using odd parity. The rule says total number of ones must be odd. 4 is even. So we have a problem. We need to fix it. How do we fix it? We add a parity bit. We want the total to become odd. Currently it is 4 which is even. Even plus what gives odd. Even plus 1 gives odd. so we add a parity bit of 1. Let us check. 4 ones in the original data plus the new parity bit 1 equals 5 ones. 5 is an odd number. Perfect. The rule is satisfied. Now the opposite case. What if the data already has an odd number of ones? Let me give you an example. Suppose your data has 5 ones. 5 is odd. We want the total to stay odd. So what do we add? We add a parity bit of 0. Because adding 0 does not change the count. Odd stays odd. Here is your golden rule for odd parity. Please remember this. If the number of ones in the data is even, add a parity bit of 1. If the number of ones in the data is odd, add a parity bit of 0. That is all odd parity is. Nothing more complicated than that. In the next slide, we will do the same for even parity. Now let us learn even parity. The rule for even parity is the opposite of odd parity. Say it with me. Total number of ones must be even. Good. Let us use the same example as before. Our data is again 1011001. We already counted the ones. There are 4 ones. 4 is even. For even parity, we want the total number of ones to stay even. Currently, it is 4 which is even. So we do not want to change that. What do we add? We add a parity bit of 0. Because 4 plus 0 equals 4. Still even. Perfect. Now the opposite case. What if the data has an odd number of ones? Let us say your data has 3 ones. 3 is odd. We want the total to become even. Odd plus what gives even? Odd plus 1 gives even. 3 plus 1 equals 4. Even. So we add a parity bit of 1. Here is your golden rule for even parity. Please remember this. If the number of ones in the data is odd, add a parity bit of 1. If the number of ones in the data is even, add a parity bit of 0. Now let us compare odd parity and even parity side by side. This is very important. For the same data with 4 ones which is even. Odd parity says add 1. Even parity says add 0. For data with 3 ones which is odd. Odd parity says add 0. Even parity says add 1. See the pattern? They are exact opposites. Here is a simple way to remember. Odd parity wants odd total. So it adds 1 when the count is even to make it odd. Even parity wants even total. So it adds 1 when the count is odd to make it even. You can think of the parity bit as a fixer. It fixes the count to match the rule. In the next slide, we will see how computers do this automatically without counting manually. So far, we have been counting ones by hand like a human. But computers do not have fingers to count. They do not have eyes to look at ones and zeros. So how do they do it? They use a tiny electronic circuit called a parity generator. A parity generator is a small piece of hardware inside your computer. Its only job is to look at binary data and add the correct parity bit automatically. Think of it like a smart calculator. You give it the data. It counts the ones. It decides whether to add a 0 or a 1. And it does all of this in less than a millionth of a second. But how does it count so fast? It uses a special type of logic gate called an XOR gate. Let me explain XOR in the simplest way possible. XOR stands for exclusive OR. But forget the fancy name. Just remember these 2 rules. Rule 1, if both inputs are the same, the output is 0. Rule 2, if both inputs are different, the output is 1. Same gives 0. Different gives 1. Let me give you examples. 0 XOR 0. Both are the same. So output is 0. 1 XOR 1. Both are the same. So output is 0. 0 XOR 1. They are different. So output is 1. 1 XOR 0. They are different. So output is 1. That is literally all XOR does. Same equals 0. Different equals 1. Now here is the magic. When you XOR all the bits of your data together, the result tells you if the number of ones is even or odd. If the XOR result is 0, the number of ones is even. If the XOR result is 1, the number of ones is odd. The parity generator uses this XOR result to decide what parity bit to add. You do not need to memorize how to build one. Just understand that it exists and it works automatically. In the next slide, we will look at the actual circuit diagram. Do not worry if it looks complicated. I will explain only what you need to know. Now we are going to look at a real circuit diagram. I want to be honest with you. This slide might look scary at first. There are boxes, wires, and tables. But do not panic. I promise you do not need to memorize any of this. You just need to understand what it does, not how every single wire works. Let me break down what you are seeing. On the right side of the slide, there is a table called a truth table. A truth table is just a list that shows what output the circuit produces for every possible input. In this truth table, there are 3 inputs labeled A, B, and C. These are the 3 data bits. There is one output labeled Y. This Y is the parity bit that the circuit generates. Let me walk you through a couple of rows so you see how it works. Look at the first row. A is 0, B is 0, C is 0. How many ones? 0 ones. 0 is even. This is an odd parity generator. Remember, odd parity wants the total to be odd. The data has 0 ones, which is even. So we need to add a 1 to make it odd. Look at the output Y. It says 1. Perfect. Now look at the second row. A is 0, B is 0, C is 1. How many ones? 1 1. 1 is odd. For odd parity, if the data already has an odd number of ones, we add a 0. Look at the output Y. It says 0. Perfect. See? The truth table just follows the exact rule we learned earlier. Even number of ones means output 1. Odd number of ones means output 0. Now look at the bottom of the slide. There is a diagram with symbols. Those symbols are XOR gates. The wires connect them together. The circuit takes A, B, and C as inputs. The XOR gates count the ones automatically. Then the circuit outputs the correct parity bit Y. Here is what I want you to take away from this slide. 1. A truth table just shows the input-output relationship. You can read it like a map. 2. The logic circuit is just a bunch of XOR gates connected together. 3. You do not need to design this circuit yourself. Only engineers need to do that. 4. Just understand that a circuit can do automatically what we did manually. In the next slide, we will look at the even parity generator. It will look very similar. Now let us look at the even parity generator. This is the partner to the odd parity generator we just saw. Same idea. Same structure. Only the rule is opposite. Look at the truth table on the left side of the slide. Again, we have 3 inputs A, B, C, and 1 output P, which is the parity bit. Let me walk you through the rows. First row. A is 0, B is 0, C is 0. How many ones? 0 ones. 0 is even. This is an even parity generator. Even parity wants the total number of ones to be even. The data already has 0 ones, which is even. So we do not need to change it. We add a parity bit of 0. Look at the output P. It says 0. Correct. Second row. A is 0, B is 0, C is 1. How many ones? 1 1. 1 is odd. For even parity, odd number of ones means we need to add a 1 to make it even. 1 plus 1 equals 2, which is even. Look at the output P. It says 1. Correct. Third row. A is 0, B is 1, C is 1. Let us count. Bit 2 is 1, bit 3 is 1. That is 2 ones. Even. For even parity, even number of ones means we add 0. Look at the output P. It says 0. Correct. Now look at the bottom table on the slide. This table compares odd parity bits and even parity bits for the same 3-bit messages. Notice something very interesting. For the same input data, the odd parity bit and the even parity bit are always opposites. If odd parity bit is 1, even parity bit is 0. If odd parity bit is 0, even parity bit is 1. Let me give you a quick cheat sheet to remember both. when the number of ones in the data is even. Even parity bit equals 0. Odd parity bit equals 1, when the number of ones in the data is odd. Even parity bit equals 1. Odd parity bit equals 0. That is all you need to remember. Even and odd parity bits are just opposites of each other. In the next slide, we will finally see what happens on the receiver side and how errors are detected. Now we have reached the most important part of this entire lesson. So far we have been talking about the sender side, the person or computer sending the data. But what about the receiver? How does the receiver know if the data got corrupted? That is where the parity checker comes in. A parity checker is a circuit on the receiver side. Its only job is to check if the received data follows the parity rule. The parity checker asks one simple question. Just one. Does the total number of ones in the received data, including the parity bit, match the agreed rule? If the answer is yes, then no error is detected. If the answer is no, then an error is detected. Let me show you the examples on the slide. Example 1. The transmitter sends this data. 111000111. Let us count the ones together. 1, 2, 3, 4, 5, 6. 6 ones. 6 is even. The transmitter used even parity, so the data is correct when sent. Now the receiver gets this. 111000001. Let us count. 1, 2, 3, 4. 4 ones. 4 is even. Wait. Both are even. Does that mean no error? Look carefully. The receiver got 8 bits. The transmitter sent 9 bits. Actually, let me correct that. The slide shows the receiver got a different pattern. The point is this. If the rule was even parity and the receiver counts an odd number of ones, then an error happened. In this example, the slide marks it as error. That means the number of ones changed from even to odd during transmission. Example 2. The transmitter sends 1110010. Even number of ones. The receiver gets 11101110. Also even number of ones. The rule matches. So no error is detected. But here is something very important. I do not want you to miss this. Parity checking is not perfect. What happens if 2 bits flip during transmission? For example, a 0 becomes a 1 and a 1 becomes a 0. The total number of ones might stay exactly the same. Even stays even. Odd stays odd. The parity checker would say no error. But an error did happen. This is called a limitation. Parity can only detect odd numbers of bit flips. 1 flip, 3 flips, 5 flips. It cannot detect even numbers of bit flips. 2 flips, 4 flips, 6 flips. Despite this limitation, parity checking is still used today. Why? Because it is simple, it is very fast, and it is cheap to build. You will find parity checking in computer memory, in simple data transmission, and in many communication systems. In the next slide, we will look at a complete example of a 4-bit even parity checker. Now let us put everything together with a complete example. This is a 4-bit even parity checker. Do not let the name confuse you. 4-bit just means we are working with 4 bits total. How are those 4 bits divided? 3 bits are the data bits. We call them A, B, and C. 1 bit is the parity bit. We call it P. So total bits are A, B, C, and P. That is 4 bits. What does this checker do? It checks one thing and one thing only. Is the total number of ones in A, B, C, and P an even number? If yes, the data is considered correct. If no, an error is detected. Now look at the truth table on the left side of the slide. Let me walk you through each row so you fully understand. Row 1. A is 0, B is 0, C is 0, P is 0. Count the ones. 0 ones. 0 is even. The check output is 0. 0 means no error. Row 2. A is 0, B is 0, C is 1, P is 1. Count the ones. C is 1, P is 1. That is 2 ones. 2 is even. Check output is 0. No error. Row 3. A is 0, B is 0, C is 1, P is 0. Count the ones. Only C is 1. That is 1, 1. 1 is odd. Check output is 1. 1 means error detected. Row 4. A is 0, B is 1, C is 0, P is 1. Count the ones. B is 1, P is 1. That is 2 ones. Even. Check output is 0. No error. Row 5. A is 0, B is 1, C is 0, P is 0. Count the ones. Only B is 1. That is 1, 1. Odd. Check output is 1. Error. Do you see the pattern? Check output is 0 when the total ones are even. Check output is 1 when the total ones are odd. Now look at the Boolean expression at the bottom of the slide. It says check equals a XOR B XOR C XOR P. This is just a mathematical way of saying XOR all 4 bits together. Remember our XOR rule. Same inputs give 0. Different inputs give 1. When you XOR all 4 bits, if the result is 0, the total number of ones is even. No error. If the result is 1, the total number of ones is odd. Error. That is literally all a parity checker does. It XORs the bits together and looks at the result. In our final slide, we will see the logic circuit for this checker and do a complete summary. This is our final slide. Let us finish strong. This slide shows the logic circuit for an even parity checker. At the top, you see a long Boolean expression. It looks like complicated math. But watch what happens at the bottom of the expression. After all the simplification, the expression becomes a XOR B XOR C XOR P. Do you recognize that? That is exactly the same expression from the previous slide. A XOR B XOR C XOR P. This means the entire complicated-looking circuit is just a bunch of XOR gates connected together. Look at the circuit diagram at the bottom of the slide. You see 3 XOR gate symbols. Each symbol looks like a curved shape. The circuit takes 4 inputs: A, B, C, and P. First, A and B go into the first XOR gate. Then C and P go into the second XOR gate. Then the outputs of those 2 XOR gates go into the third XOR gate. The final output is Y. That is it. 3 XOR gates. 4 inputs. 1 output. That is parity. Simple, clever, and still used in computers today. Thank you so much for watching. I hope this video made parity easy for you. If you have any questions, feel free to ask. See you in the next video.